Cool. So welcome everybody to today's special year seminar on theoretical machine learning at the Institute for Advanced Study. Today we are delighted to have Dr. Deng as our speaker. Li is the Chief AI Officer and partner at Citadel, and previously spent 17 years at Microsoft Research, where he was the Chief Scientist of AI, the founder of the Deep Learning Technology Center, and partner research manager. He's known for his extensive contributions to automatic speech recognition, prior estimation in sequential probabilist models, and acoustic signals processing. He's perhaps best known as a leader of the deep learning revolution in speech recognition and for his work on discriminative learning of hidden Markov models and filtering in linear dynamical systems. He's an elected member of the Board of Governors of the IEEE Signal Processing Society and served as the editor-in-chief of the IEEE Signal Processing magazine and the IEEE ACM transactions on audio, speech, and language processing. He's also a fellow of the Canadian Academy of Engineering and the Academy of Sciences of Washington State, the IEEE, the Acoustical Society of America, and the ISCA, and is an author of 6 books. Today, Li will tell us about from speech to AI to finance AI and back. Please welcome Li Deng.
Hey, okay, thank you everybody. Thank you and for the very nice invitation. I'm pleased to accept this talk at the prestigious Institute for Advanced Study. Yeah, I always know that Einstein used to work here. So today's topic is from speech AI to finance AI and back. So I work on speech recognition for many years, starting from my academic career at Waterloo in the Greater Toronto area. And then I was so fed up with this old field, so I decided to move to industry to see, whether the bigger impact can be made. That was about 20 years ago. So at about 10 years ago, while I was still continuing working on various generative models of speech, including hidden Markov model and many versions of the generative models of speech based upon articulatory dynamics, based upon motor control, all these physical properties, and they use the Bayesian kind of Bayesian network, a deep Bayesian network to represent speech dynamics with the hidden a whole bunch of hidden dynamic processes. I actually gained tremendous amount of understanding of the process of speech generation, and then I created statistical models based on dynamical theories, many layers of dynamical theory to do speech recognition, and only to find that we reverse that direction of information flow. That was very much motivated by Professor Jeff Hinton, of deep learning thinking. Using deep representation of the signals, and then much greater breakthrough was able to be achieved. So I'm going to go through part of this process of learning and research, and then tell you some of the historical events about how speech recognition revolution occurred about 10 years ago. And then later on, I move on to do finance AI after everybody saw that the direction of speech recognition is pretty much set up. You get big data, big label data, and then use a very large amount of compute and big model, and the problem is it's virtually solved in terms of research issues. So today's topic is to first give you a brief overview of this set of historical research and the event that led to the big impact of learning in speech recognition field. That happened about 8 to 10 years ago. And that was about 2 years of very intense work within Microsoft. that I was sort of a big part of, that actually eventually culminated in speech recognition, completely dominated by deep learning. And then also I'm going to give you a little bit high level of survey about what other kinds of problems in my field of research that subsequently have been impacted by deep learning, including dialogue systems, computer speech understanding beyond recognition, and I'm probably will skip computer vision and some other areas. I will go a little bit into natural language processing and machine translation. And those are the areas that I've been working on. I was working on at Microsoft before I moved to finance AI. So about 3.5 years ago, I decided to leave Microsoft to attack somewhat more challenging problems of artificial intelligence using kind of deep learning concept and techniques, and in a completely different field. At that time, I thought that was the case, but it turned out that there's a very quite intimate connection between these various fields, and I can share some of the technical challenges that are quite unique to financial investment industry, as well as similarity to some of the old fields that we have known to be impacted, very strongly by deep learning. And finally, I will give some sort of highlight about, some of the new insights that I have learned from this new industry and how they can be back to benefit and advance speech and language technology in this deep learning era. But revolution is still ongoing. Many people ask me, what the future direction of deep learning is. So my actually current feeling is that the revolution still keep going, especially in the in certain application areas where the large data is available and also the output is reasonably clean. And if they are not clean, there are no noise either in the input or the output. Like in the financial world, people have to sort of make new kind of discoveries as well as inventions for some theoretical aspect of the deep learning in order to tackle those problems. And the problem is far from being solved. So I asked the question, for this kind of presentation. First, whether AI can transform the financial market. Okay. And of course, my answer would be yes. Otherwise, I wouldn't be able to, I wouldn't be able to accept it at the top of this type. And then to justify, my answer, I would like to survey, some of the speech industry's revolution that happened over the last 10 years, and then show you the, the similarities and differences between these two industries. And due to time limit, I will skip some other applications. So let me start with modern AI, or namely deep learning. I always call deep learning to be modern AI. Some people don't agree with me, but most people do, but especially in the industry. They believe that modern AI really is dominated by deep learning technology. And sometimes it may not be neural network, right? So there are a lot of concepts, but the key here is that the representation have to have some very sophisticated architecture, not just simply in the old days we use a hidden Markov model. We thought that it's a very sophisticated model in terms of theory. There's a lot of theoretical problems in hidden Markov many years ago. I studied them all, and then I applied them in area and also in many other areas as well. They are just not sufficient to solve big, large-scale problems, right? So the deep representation is really the key. Whether it's neural net or otherwise, that's I think open. So this is actually what the whole bunch of slides that I cut off for this presentation. I want to give some other talk. But there's a long history leading to this workshop that happens actually about 11 years ago, where we actually, so before that, the workshop, we actually, I myself actually invited Professor Jeff Kington to come to be my consultant during 2009. And even before that, there was a lot of discussions, especially during my academic years at University of Waterloo. It's just really part of the Toronto area. So so there was a lot of neural network approach tried. For example, my first PhD student actually used neural network, a dynamic neural network controlled by hidden Markov model, to do recognition, even for small tasks at that time. I mean, that was 1994. And the results just can hardly compete with the hidden Markov model. Okay, and then we understand at that time, like the 20s, that was 25 years ago. It's very hard to understand why couldn't do as well as hidden Markov model. Partly because there was some nice theory to show that neural network and certain kind of neural network and hidden Markov model are kind of equivalent to each other if you make a neural network, especially simple. Right? There's some very nice work at that time. But once you apply that neural net practical scenarios, at that time we were doing digit recognition, right? Exploring neural net, and now we understood the reason in old days. Number one, the data is very small. Number two, we didn't at that time in 90s, at least during my time, I was academic. We didn't really use the mini batch kind of training. Usually either we use the full batch training or we use stochastic descent, just using frame by frame or single sum by single sum. And that is actually very nice, middle way of doing the learning using mini batch, and that's a very, very important aspect of recent advance. So there are a lot of controls that can be imposed on the learning, and the deep and back progression was there also, right? And it's just data isn't big enough, the training paradigm isn't right, and then of course at that time there was no GPU, right? And then it's just the results could never compete with the Markov model. So I pursue a lot of probabilistic model, dynamic system model, modern physical systems, for speech production, computation models for those. And then at that time, actually, we did get some very, very strong result for research tasks. With the deep representation in terms of the generative model, and in order to model dynamic system for speech articulation, these are all preceding, preceding this workshop. And then we did produce the state-of-the-art result using, I think at the time it's about 6 layers of generative model. That was published in IEEE transaction. But we used just basically using variational learning method to approximate the learning algorithm because speech is dynamic process, so you get a lot of loops, heavily looped Bayesian network, and a lot of approximation need to be made to make learning feasible. But the representation is right. The learning wasn't right because the imposing some constraint about articulate dynamics required that the matrices in the dynamic system being sparse, not full matrix like neural network, and that's one of the big differences between the current neural network and those deep generative model with dynamic system there, and that was a very big difference, and that difference makes the learning to be not as efficient as the just standard backpropagation. But anyway, so I was able to create the state-of-the-art result at that on this the task, standard speed task called the TIMIT, TI and MIT put together, and this is a very famous. It's actually bigger than MNIST in image, right? So basically, in that the task, everybody was using that. It's a little bit like it's less than ImageNet for image recognition, but much bigger than MNIST, somewhere in between. Maybe a little bit like CFAR, maybe somewhat bigger than CFAR. So I remember in that task, the training set has about 4,600 sentences. That has about, you take the frame into account. It's about 1.17 million, a little bit over 1 million training samples. And then it was on the phone recognition. So at that time, I call the hidden dynamic model, deep hidden dynamic model, produced virtually the state of the result, beating all the hidden macro model. And then, but the learning and the decoding is much more complex. If we use the Bayesian network, deep Bayesian network, dynamic Bayesian network to do the learning and to the decoding. So a lot of approximation needs to be done. And then it turned out that it's almost impossible to put that into Microsoft product. So at that time, I think in 2008, 1 year before that, I reconnected with Professor Jeff Kington, I think at NIPS conference. And then he actually told me that, wow, I haven't seen you for a long time. What's the progress? We exchange our research, work. So I told him I was working on this, this Bayesian network, deep Bayesian network dynamic model. And he shared with me. He said that, wow, it didn't work neural network a long time ago, but I should read his 2006 paper. That was 2 years earlier he published, and most of the people didn't really read that paper. I didn't read that paper until he told me, Lee, you should read that paper, and that was called the Deep Belief Network. So I went to read that. I returned to that was 2008 at NIPS conference. So I read the paper. I realized that, wow, that's also generative model, and the difference between that model to my current model at that time, right? The Bayesian network model was that there was no dynamics in his. I mean, the paper is just a static, many layers, and there was nice proof that. I don't know how many people read that paper. That was in neural computational. The title of the paper is sort of a fast method of learning deep belief network. And the paper is pretty hard to read, actually. If you try to read that appendix, you get confused. Right? But I think he told me that the appendix was actually, the theory was provided by one of his postdoc, Tae-Wai. And it's very nice result. I mean, there was a theory, they use approximation as well, but it's the generative model. It shows that a surrogate of objective function. It can prove that every time you increase, it's essentially stacking of restricted Boltzmann machine, RBM, and then they're using constructive learning. And then when you stack up one layer by another, you actually can get. And he was able to prove that this surrogate objective function can have monotonic increase. Very nice. So I read the paper. I couldn't quite understand the proof. So we have some discussion, and he ended up coming to my place to do consulting for me. And then we actually, so the paper was only on MNIST, it's an image, and there's no dynamics there, right? So of course there's no complexity in terms of putting the loop into the system to do speech recognition. So I said, well, come over. So let me try that to speech recognition, so we can do frame by frame, without having to take into account, so that problem becomes similar to image. But if you want to put speech together, there's a variable length, there's dynamics there, and there are a whole bunch of things we need to put together. And then an easy way of doing that is to put hidden macro model on top of this, right? So we explore that type of comparisons between two types of model. Actually, I personally found that at that time, the error are virtually the same now for that particular task, about 1 million frames as input data. So I think the accuracy is about 75 versus 76, somewhere around there. It's comparable. I was almost give up this type of research, but I was kind of lucky enough. I have been doing this research for so long. And also for that particular task, you know, in the academic community, people, you know, you can call it cheating or not, right? When you publish a result, you actually, you know, run tests many times, right? You know, so I was running this kind of test data for so long, I can actually remember almost every single error for that task with about 7 test tokens. You know, I kind of know what kind of distributional error it is, right? Sometimes you do some cheating on your task, you understand what they are going on. And of course, you know, you can never put that system into practice, right? You know, especially for finance. But for spiritualization, the problem isn't as bad. I'm going to show you a little bit different field. You know, sometimes we do a little bit cheating, like looking into the test data, and you understand what they are. So I just happen to remember almost, you know, the error pattern, distributional errors for all the speech classes, about that 7.7 thousand, a little over 7,000 test tokens. So I look at my generative deep models of results, and I found that, wow, you know, the error patterns are very different. Although the error rate overall are similar to each other. That means a certain kind of sounds, especially short sounds. You know, some sounds are very short, like, you know, very short sounds. And that deep belief network makes a whole bunch of mistakes, whereas my dynamic model actually, you know, make very little mistake. Where in some other sounds, you know, with many kind of complex structure, and deep belief network is doing a lot better than my generation model. We call it deep hidden dynamic model. So for that reason, I realized that, well, there's something really going on, that deep belief network. And if you turn deep belief network into, you know, app propagation on deep belief network, you actually turn out to be something very similar to deep, you know, neural network. So I was able to sort of look at the error patterns and identify the uncorrelated this between the two set of models in terms of their recognition error. But this kind of comparison now become, you know, relevant to finance world. Well, I'm going to show you a little bit more down the road. So and then we started, you know, doing. We thought that, well, you know, different ways of doing deep learning, either generative model or maybe perhaps just turn deep learning into neural network. You know, would be very useful. So they actually, so University of Toronto actually did this kind of backpropagation training for the for this, you know, deep network. And I think at that time, 2009 or maybe even 2010, nobody talked about deep neural network. Everybody talked about deep belief network. So it's abbreviated by DBN, right? Deep belief, for those of you who know the history. And then the pre-training and fine-tuning concept all coming from there. So DBN is pre-training, and then backpropagation is fine-tuning. And then DBN, and I was asking Jeff, I said, well, why do you call it DBN, right? You know, it's supposed to be DBN at that time stands for deep, so dynamic Bayesian network. That's exactly the kind of model that I was using. I make them many layers of deeper. So it should be, you know, deep Bayesian network DBN. What do you call it? Deep belief network is DBN. He said, well, and he said he purposely chose that overloaded word in order to show that deep believe that eventually they have to be dynamic Bayesian network. And then I think, you know, show me that, you know, look at, you know, how the comparison between the two is pretty much the kind of things that he was very. So in the beginning, they're very similar to each other. So once you add more data, you add more power, computing power, make the model bigger and bigger, then the DBN, deep belief network, adding backpropagation, which turns DBN to be deep neural net, is doing substantially better than Bayesian network. So in this you know, workshop, we discussed, you know, a lot of issues related to model and deep Bayesian network. I think he gave a tutorial. I gave a tutorial there. So I don't know. Maybe many of our audience here may be too young. And actually, that workshop was filled with the audience. And then, but at that time, there's no large vocabulary speech recognition. It's all phone recognition using, you know, timid, you know, the database that has about 1 million samples. is the kind of standard task at that time. People talk about all this a little bit like MNIST, right? In speech, and the people have some interest in that at that time. And then I myself, I realized that the error patterns are very, very different, and I should throw away the generator model at that time to make it quick. In industry, right, we always look for the quick way of making impact. So we actually hire, two of his students to be our intern, bringing in all the GPU expertise. And then I had to sort of convince my manager at that time at Microsoft to buy GPU. And everybody in my organization at that time, Microsoft Research, said that, oh, don't waste your time. You have budget, right? You can spend $20,000, throw away, blah, blah. And then, why you throw away $20,000? You might as well just buy something cheap from Fried Electronics, right? Play around that and throw away, that's fine. We are research organization. It turned out that those 3 GPUs I ordered at the advice of Jeff Kington, he actually gave me the spec, what GPU you should run, using, to do recognition to the image, whatever. So I followed his order to buy fairly expensive GPU compared to the kind of cheap ones that, my engineers will recommend, ready to be thrown away. But now those 3 GPUs become probably, I think they are now probably in museums of Microsoft somehow. It's initial GPUs that actually started, Microsoft deep learning as early as 2010. But anyway, so we work very hard together with, and Professor Kington also came to my place to be my counselor again 1 year after that, 2010, and then together with 2 of his students. And then we work very hard together with our speech product team doing a large scale. At that time, we didn't make things public because we never realized that our competitor can catch up so fast. And we start. I put all my team, tons of resources into deep learning for deep neural networks and making that bigger and bigger. And then along the way, we discovered that I think Toronto people also told us independently that they found the same thing. I think somewhere within 2010, especially as Microsoft with the speech recognition product team, we discovered that with the large amount of data, we don't even need to use the VPN to do pre-training. That was fairly complex algorithm, and partly because those people in product team don't understand how to train them. Well, I was the only one who actually know how to train them, because I think Jeff didn't share the code, of the code for, and he actually told me that he wrote the code by himself. I fully trust. But I happen to run. I happen to use MATLAB as well, so I was able to to not only duplicate his result in MNIST, I was also able to change that into I just did quite a bit of the code in order to apply that to speech, because there's a dynamics involved, right? So I make put the Markov model there. But anyway, so we worked kind of in for the whole year. In 2010, we discovered that with large amount of data, it's okay not to use pre-training part, but with a small amount of data for timid tasks, that kind of pre-training is still important. Right? It regularize the neural network, and then I think we worked very hard also. I think we did publish a paper in 2000, at the end of 2010, in the workshop. I think the paper wasn't accepted in the NIPS. At that time, 2010, nobody still did neural network. Right? So we put that into one of the workshop, large vocabulary, speech recognition with, I think with his students who contribute very significant in GPUs in some of the learning, and then we published that one. And then most people still didn't take that seriously at that time, 2010. But we all know that within Microsoft at the end of 2010, deep learning is really, really powerful. And then entire speech team, they even reorganized their maybe part of their people there, in order to full-scale implementation. So 2011 and then part of 2012, we just pushed that deep learning to be bigger and bigger. And then we decided that I think our upper management decided that now the time is ready. I think partly because I think Google started working on that also when Jeff Kington started doing consulting for Google. Because I was asking him to come back, to do consulting for us continuously. There are a lot of arrangements we made, and then he said, no, I'm doing academic work, and he actually told me that he even was treated as an intern at Google, working with Jeff Deng, or maybe with I don't know whether Angel Ng was there as well. But anyway, so he promised that he never sent there, the good student our company. That's 2011 or something. But anyway, so at one time I think Alex Krashevsky, who actually did this computer vision revolution, and we discussed that for him to come over to my intern as a master student, right? So, but at the end he said, "Wow, he has some more important job to do." Right? It turned out to be ImageNet. Otherwise, the whole history will be different, right? But anyway, so this is the New York Times full page. I think this is probably the very first real, PR event from Microsoft showing off learning power in speech translation, more than speech translation. So we thought that speech translation sometimes is hard to do public demo, right? It's not like image, we can do demo. And then you have to create. So I was, part of this planning as to how to make deep learning publicized, for the sake of, Microsoft reputation, for the sake of technology innovation. And then this, Rick Rush, he's the head of, Microsoft MSF head, overseeing all MSF research. He's very sharp. He decided that, well, if technology is ready, let's do translation, because translation is visible. You can talk, you can translate, people can see. It's like, more like image, what people can see, in the audience. So we actually make use of deep learning speech recognition on his speech. It turned out that, he was so cooperative. We trained him. And then the error rate at that time, we did test, before he went out to do this public demo, it's dropping down to 7%. Well, normally at that time, like that's about 8 years ago, error rate, standard speech recognition error rate for what's called spontaneous speech, like the way he talked, on the audience, in the podium. Typically, that was, usually it's quite high. It's about usually at that time it's about 20-some%, right? And then for him, he was very cooperative, so error rate actually was just as low as 7%. He said it's ready to go, and then we hook up speech recognizer into machine translation system and then speech system. So whatever he talked in English now gets instantaneously translated to Chinese, speech. So people in the audience, about 3,000 people in Kington at the time, was able to listen to him. And then I saw that some people are having tears, right, coming down, saying, "Wow, with this technology, we don't need to learn foreign language anymore, right?" And then somebody even said that now, I think this is one of the foreigner, in China, maybe from Europe. He said, "Now I can speak with my my mother-in-law because he married with a Japanese woman, and then her mother doesn't speak Japanese, doesn't speak Chinese, or doesn't speak English, right? Now before we couldn't communicate each other, but with this technology, everybody can in the world can communicate with each other without having to learn, painstakingly, the foreign language." So that was a big event. And then this is John Markoff. He's the New York Times reporter. I think he's still doing some writing. Actually, he flew to Seattle to interview me, and he told me that he also interviewed Jeff Kington in Toronto at that time while writing this article. And I think he told me that both of us told him that we never patent anything out of this technology shown in the demo, and that was true at the time. Yeah, we may have filed something, maybe not directly related to this particular kind of learning, but in general, we thought that a lot of algorithms, deep learning, they were already well known, nothing else to patent. I think John Markov wrote that part of sentence into this article. And if you haven't got time to read this article about 8 years ago, you should read it. It has a lot of details about the demo, about how deep learning started, from Microsoft, and then I think at that time, ImageNet result came out. I think he didn't. I don't think he mentioned that speech recognition success was about almost 2 years ago, earlier than image recognition. The image, ImageNet result also quoted in this article, and that would just come out about probably 1 month ago. So image is a much bigger community than speech. I think image net actually very often people think about image that is the landmark in deep learning. I personally feel that speech probably is earlier, but in any case, they are very similar. The similar kind of success between the two fields. But anyway, so this is the architecture that we use in this demo. So in this demo, we use this architecture for speech recognition. So I think at that time, and the layers, we used them up to about 7 to 10, somewhere around that. And then another thing actually I found along the way was that, so as I told you that from this timid database, the training set is roughly think about to be 1 million samples. Whereas when I put the hidden layer in this net, typically 1 layer I can put as many as possible, but usually 2,000 is turn out to give the best result. So we put 7 of these deep neural network layers, one with 2,000. So every single layer I got 4 million parameters. Right? My training data has only 1 million samples, and then to my surprise, when I have 1 layer, I got good result. And I got 2 layers that got about 8 million parameters. As the result getting better, I go all the way. I remember in that example, it's 13 layers. So 13 layers. How many samples? 4 million for one layer. 13 million. It's about 15 million parameters of the model using just 1 million samples, and then the result is getting better and better. But after I think I remember 11, 13 layers, and then performance accuracy still flattening out. It's just amazing, right? So at that time, I thought that wow, the standard machine learning theory has to be broken, right? You get about how many, 60 times more parameters than the number of training tokens. You still get a good result. It doesn't never overfit at that time. So at that time, I was thinking that wow, the theory people really have to do something about it. But I was so busy, doing. Making the practical and recognized work, I just ignore all these issues. I say, talk with. So actually, yesterday I was synced up with my previous colleague at Microsoft in the speech product team, who is now, and then he actually took the success of deep learning from speech at Microsoft. He was in speech product, and he brought the whole thing to Amazon. That was about this time, right? And then he's left, and then Amazon, he told me in the beginning, Amazon didn't quite believe, and he has to convince Amazon to do it. And now Amazon everywhere is deep learning. And then at the same time, I think Jeff Kington told me that he has another student, the one I kind of knew, but I didn't really know him well. It's not the same one who he sent to share with us deep learning experience, especially with the GPU. Now deep his name, and then Jeff Kington sent him to Google, I think during the summer of 2012, and then he practically duplicated all the results at Microsoft. Once you know certain things work. So one of the experience that I learned from here is that if you don't have confidence that something is going to work, you usually play that around, and it doesn't work well, you give up. Like 90s, I tried it, it never actually worked. But once you know something works, then even if you get all the stumbles, you get the momentum going, right? It has to make work. If you know that, somebody, at Microsoft make, using this approach, get larger scale system work well, then of course, I would try very hard to make image network too, right? But at that time, I didn't. I mean, if I have this, vision people with me, I probably would do the same thing, right? Just do the vision and vision. The difference is very, very small. In terms of, we have analog data, and the speech. Many people think about speech one-dimensional signal. That's wrong. Speech really is two-dimensional signal. I'm going to show you a little bit later. In order to really represent the speech, you have to use time and frequency together. It's more dynamic pattern. In a certain way, it's somewhat more complex because in one dimension you have elasticity. The other dimension you have frequency. It's a bit like an image, right? So it's a bit different kind of. But vision is more complex. You have more, time varying image. You have one more dimension. But in terms of dimensionality between image and speech, they are really the same. Many people actually just use the graph of speech. I'm going to show you a bit later how it looks like, how to interpret speech in terms of image. From there, you can understand the speech a little better. So, but anyway, so this diagram on the right-hand side shows the progress on speech, starting from 1993. This is the much bigger speech database. And the breakthrough also occurred at Microsoft at 2010. We actually, my colleagues, at Microsoft Research, as well as the product team, they actually reduced that particular error, error rate, roughly from 26% to somewhere around 12%. And actually, by accident, that kind of reduction is very similar to ImageNet. I mean, so sometimes, I don't even have to remember image result. The order of magnitude reduction is the same, really. It comes 20-some% to, to 10, somewhere around reduction by about 30 to 30%, somewhere around, just one single experiment. And then for regression demo I showed earlier, the error rate dropped down to 7%. That happened in 2012. But now this task, the error dropped down below human error. I think for inspection rate, the same kind of task. The error rate dropped down to 4% or something. Very, very similar to ImageNet result. And then academic paper have been written. Actually, I wrote this paper with Jeff Kington on all the experiments we have done. There's a good summary about how to motivate this type of deep representation. And this paper also probably summarizes some of the work I did prior to this deep learning, also deep representation with the Bayesian networks and dynamics. It turned out that the dynamics in Bayesian network at the lower level actually turned out, which is pretty crucial in terms of physical property articulation. Should be if I did not remove that part of connection dynamics, I wouldn't be able to get a nice algorithm to train the model. I have to use variation learning for Bayesian network. Well, you do variation learning and then you approximate them, you cut it off, you learn it, and then you iteration. And without doing this, nothing is the algorithms become too complex. Whereas the deep network just by default remove them altogether, just using neural dynamic sort of hidden macro model at the top layer. Therefore, there's no loop into the whole system. All the learning become very easy, and backpropagation can apply to it. So a lot of learning process has been going on throughout this work. So now I want to say a few words about the connection between speech recognition system and finance system. Well, maybe I can only due to the time, the limited time, I can only say a few words about the comparison. So if you look at the speech recognition system in the old days, in the old days, I mean 10 years ago, before deep learning coming into the picture, there are many components, right? So you have acoustic model here, that's typically done by hidden macro model. And then lecture model, I'll ignore that part. And the language model is all trained, it's prior, right? So you have combined language model with the acoustic model and then come up with the decision. And language model at that time typically was done by Endtoend model. It's a macro process, it's symbolic macro process, and they are learned completely differently. So we used a labeled speech data with the acoustics and the corresponding labels. You get text and speech correspondence. You learn acoustic model, hidden macro model. Whereas the language model is all done by language. It's just language by itself. And then you multiply the probability together, and then it becomes the joint score. And then to do that, you have to scale the model with some magic number. And this, so one of the effect, the very strong effect of deep learning is that you just ignore all these magic parameters. So a few companies actually who used to dominate speech recognition, and now they're in big trouble, right? Because they used to have a lot of the magic numbers, those magic numbers are not like hyperparameters. They're in a way they're hyperparameters, but those hyperparameters are very hard to justify. Right? You multiply two probability, you have to scale this probability by a factor. Sometimes for different tasks by a factor of 8, sometimes by 15, sometimes by 20. So those magic number, that's why commercial systems usually were dominated by big companies, because small research groups, they never actually get to know how to tune those parameters. They're all right. There's no theory there. Right? When it's a Bayesian network, combine different source information, you have to scale them in a very strange ways. So those are the old days, right? Hidden Markov model, N-gram model, and then you have to do the kind of first sophisticated search. But actually, it turned out that the current search algorithm with the deep neural network are not very far away from the old search algorithm. That's the part that industry has a lot of things to control. They have audio, frames, state, phoneme, word, sentence, all the way meaning. So this part is modeled by language model, and this part is modeled by acoustic model. So this is the state of art up until 10 years ago. But nowadays, we still have language model and acoustic model. Since both are represented by neural network, they can be learned jointly altogether, right? So that's called end-to-end learning. You don't have to distinguish acoustic model and language model. You just learn them all together if you have large amount of data, okay? So like Google, for example, if you use the YouTube, you see acoustic transcription for whatever people say. And since YouTube has a very large amount of data, they don't have to do to train language model separately. There's enough acoustic data, therefore whatever is corresponding to acoustic event get jointly trained. So you can do end-to-end training all the way. But in most other kind of tasks, you still are not able to do, because the corresponding speech and language data are not large enough. So it still makes sense to train language model separately. But at the end, when they do the search decoding for real time, the way to combine them together. If you also use the neural network to represent language model, then the search process become unified. It's just much easier. So engineering, so deep learning not only gives better result, but also it simplifies the industrial system there, because you can throw away a lot of magic numbers in the old system. Right? So I give one of them. There are many of these magic numbers, and it's very hard to justify. Whereas a neural network, hyperparameters, sometimes you can still justify them, right? Maybe not as easily as you would like, but still can justify them, because how there are even automated auto ML to automatically learn hyperparameter, whereas in the old days, there are a whole bunch of magic numbers there. There's just no way to do it. Human has to be involved. So there are big contributions of deep learning. Number one, it drastically reduced recognition error. And number two, it simplified industrial process. But of course, initially investment has to be large. You have to buy GPUs. You have a lot of resources. You have to train people in a different way than in the old days. So now I'd say a few words about finance, connections. I'm going to skip most of my. So Keith, you told me that the emphasis for this lecture is more on speech part. So in finance, it's very similar, right? So in speech recognition, you have a few modules, language model, all this module, and then you combine the information here, and then you just get the output. Whereas in finance model, for those of you who know, if you don't, then don't worry about it. Okay. So there's a very important model, alpha model, risk model, general cost model. You put them together, you construct the optimal portfolio, and there's no theory involved doing this, and then you execute. So that kind of combination, of different modules integrate all together to optimize the combination of various models to come up with this, the final result. It's very similar to portfolio construction in terms of combining modules. But now, in the old days, these are all separate from each other, right? And then you go together, and then neural network unify them to get unified sort of end-to-end learning. And so far in financial world, that hasn't happened yet by the time I joined. I'll go through a little bit of language model. Oh no, sorry, natural language processing. The time is a little bit short here. Yeah, so I'm kind of fortunate enough to be able to finish this book talking about natural language processing. So conversational language understanding that make use of neural network speech recognizer, the architecture. Now, everything in this book, as well as in practice, state-of-the-art system in all these natural language processing tasks are now based on neural network. I believe if you don't use this deep learning in natural language processing, typically you don't get people accepted, right? It's just the opposite to many years ago, a few years ago. So so this is the chapter talking about dialogue system, and that's a very interesting new area of deep learning in natural language processing. So the key is that the input actually, it can be speech input or it can be text input, and then you have to understand, not only recognize the words, right, in the speech, but also have to put the words into right slots, and that accomplish natural language understanding. And once the slot is filled in, then the speech is understood, right? So to do that, you can only do that for limited tasks. If the task is open-ended, there's no technology at this point doing that. And unless I try to do open tasks, open domain, speech understanding is still research still ongoing. But with the finite domain, like if you want to just book flight, then you can write down all the schemas there. And then once you fill in the slots in the schema, you have full understanding of the sentence. Well, that's actually the difference between understanding and recognition. Recognition, you don't have to have a task. You can say anything, right? Everything become and that was about 30 years ago. Speech recognition was a little bit like speech understanding now. You have to have a task. You have digit, right? Because if the number is small, then you can recognize them right. If you open too many, then mistake or came along. But once deep learning came into speech recognition, actually even hidden Markov model time, people were already able to do open domain speech recognition. Now for natural language understanding, so far, from at least from the open literature, you can still see that to have a complete accomplishment of natural language understanding, you have to limit the domain, and the experts have to be involved in designing the domain. And that's one of the reasons why natural language processing still has lots of jobs. Right? And speech recognition probably less, right? Because you have to get experts involved to design understanding tasks. And then for different tasks, you have different ways of doing, understanding. But now the approach for this kind of task is dominated by deep learning. So in this chapter, I show you a few of these architectures here. Another very important breakthrough over the last, I think that this machine translation breakthrough started 2015 or 16, right? But now, it's completely dominated by deep neural network, and that's coding, decoding architecture. Actually, it was done by one of my interns. While I was doing speech recognition, he was part of our intern, learning how to do deep learning in speech recognition. And now he provided, once he joined Google, he provided breakthrough, architecture for machine translation, encoding, decoding architecture. And then there's another very important task, which is also summarized in my in one of the chapters in the book. It's a question answering. So you provide the question, that's the input, and the answer is the output, right? Now for this task, all of the breakthrough lately came from deep learning. So I put all these beautiful pictures as so sentiment analysis now is all done by deep learning, and this is very important, right? For Amazon, for book review, for product review, sentiment analysis play a very important role in practical, and also in finance. People like the stock or people don't like stock. Whether the sentiment is good or bad really affect the stock market, and sentiment analysis plays a very important role there. So natural language processing techniques based upon neural network now become very widely used in many different fields. And there's another deep natural language processing task called image to text conversion. But before deep learning, people never thought about this task being possible. You have a picture here, and then the computer create a sentence for you, right? And that task got very popular in 2016. I think just within one I think I think it's NIPS submission, right? All of a sudden, I think about 6 papers on the same topic were presented. I think all 6 papers were accepted during the year. So I remember Microsoft, we are actually working on this task, and then Stanford was working, without knowing each other, right? So everybody realized that once they knew that translation, is successful in deep learning, people have very simple ideas. Say that, well, rather than using the final state of the encoder to summarize the source sentence, if you replace that sentence by an image vector, then the same thing will happen. You can generate the languages. The idea is very natural. Anybody who work on machine translation will know that image to text problem is really the same problem as translation problem. So I think the 6 group of researchers at that time, 2016. I think many of those probably work on translation at the same time. Including I think people also work on a Stanford group, and then our Microsoft. We all realized that, wow, we can do that, and then everybody gets similar kind of result, and that this become very popular task now. I think it has something to do with deep fake. There are a lot of quite a number of other new techniques later on are based upon some early work here. So now let me. So I think the time is up. 1:30 in your time. So how about let's just stop right here, since I finished all the speech stuff and the finance. I don't think I'm going to spend any time on that. Okay.
You actually have another 5 minutes if you want.
Okay. So let me go quickly. Okay.
Yeah.
So let me use the 5 minutes to go over the remaining set of slides. So the technical challenge of financial investment, like stock market prediction, they're quite different from speech, the one I showed you earlier, but it shares a little similarity. I'll show you some key differences. So the number one key difference is that there's a very large amount of heterogeneity of data. So in speech, our input is acoustic, right? And then for translation, the input is text and the output is, is text, right? It's a very limited style of the data. So typically you have 1 or 2 types. Whereas in finance, we have tons of different kinds of data. This slide shows you all sets of data. There's a text data, there's speech data, because all the news media talking about sentiment, the interview data, conference call data, all this video, image data, is useful for finance as well. If you take a sector image, right, and then it can tell you, whether your parking lot is good or not. That becomes part of the thing. So the size of the data, the type of data is so much bigger. So you have web traffic, it becomes part of the input data, and then the sensor data, image, weather forecast, geolocation, where people are, it affect, how products are sold, right? And then corporate data, and then supply chain data, banking rec, all this business data as well as social media. So the type of data is just huge. And then the point I want to make over here for this presentation is that neural network, deep neural network are ideally suited to integrate diverse type of data. Whereas if you use shallow learning in the old days, those data have to treat it very differently, and then you have to use the magic number to combine them in order to come up with the final result, just like hidden macro model. So deep learning really is ideally suited for this aspect of finance. The second challenge is the signal-to-noise ratio. The noise level tends to be very, very large compared to all the speech problems, right? So you may think that if you put the speech recognizer in the helicopter, you think that, wow, very often but nowadays the problem is pretty solved, right? If you get the right microphone there, even if we get I think in the helicopter condition, and signal ratio is typically 0 dB, right? The noise is almost as loud as if you shout, you get the similar kind of energy. But in finance data, signal is even much lower than that. And then there are many techniques in finance world that can help to handle that kind of problems. It goes beyond the standard technique of deep learning. For one example, I would quote that how to do smart regularization to handle the very large amount of noise. And then the noise is reflected themselves not only in the input but more important in the output. Because most people think that well, that's what I thought before I joined the finance company. I thought that it's just the output. The output is maybe the returns for particular stock each year, because you get the data there, right? The return is in the past. Actually, turn out the return it really is not signal, right? Because return is incorporating all this hype information, right? So if somebody make a tweet, right, some important person make a tweet, the stock can go up, and then the next day it comes down. The intrinsic value of the stock may not change. It may not be reflected. You don't even know, right? If you just look at the data, market data, that's misleading in many cases. So therefore, there's a lot of noise in the output as well. So we found that a lot of techniques that are effective in handling small data but clean output data, have some effectiveness in dealing with large data with noisy environment, like how to do regulation. And it's very, very different between anything that I have done at Microsoft. And then the third challenge is non-stationarity with adversarial nature. So some of the speech is non-stationary. Everybody knows it's like it changes. The non-stationary means that for engineering, for computer science, right? For mathematics, it means different. Well, it's I got city all this. For us, non-stationary simply means that the statistics, first order, second order, maybe higher order statistics, like correlation structure in terms of temporal, and they don't change as a function of time. But the mean is always changing, right? The first order statistics in speech is changing because every time you say different words, you have different kind of acoustic average. So by nature, speech signal is stationary. Financial data is stationary. Sorry, they are all non-stationary. Speech is non-stationary. It's meant for the first order, and financial data is non-stationary in both the first order and second order. But the difference between the two is that in financial data, we have adversarial nature, whereas in speech data or vision data, video data, non-stationary typically don't have adversarial nature, and that make big difference. And there are special techniques that, so Deng is one way of dealing with adversarial, nature, and then some of the techniques of deepfake, maybe how to debug, defeat and combat deepfake may have some relevance to handling adversarial nature of financial non-stationary data. Okay, so that's pretty much, I have final slide to show that how the kind of learning that I have attained during my years at finance might come back to help speech and language technology. And a lot of people, many of my friends, who are at Microsoft, this is the keynote that I gave just, I think 2 months ago in our technical conference when I received an award. They keep telling me, so Lee, you should talk about how much you learn can help our community, blah, blah, blah. And then, I have not much time to think about this except to actually tell my colleagues that I want to write a slide for that, maybe this for, so they don't want to listen to something of finance. They don't work, they still work on language and speech, right? So I come up with a few sort of guidance for the speech community, saying that given all the speech recognition now completely taken over by deep learning, and you get more data and it's getting better and better, what else they can go, right? Of course, my advice is always move to understanding, right? If you can solve the open domain understanding problem, that's a big one. But it's not very easy. Deep learning doesn't have I don't think deep learning is the final solution for that time. You have to use much more logical thinking, logical inference in order to combine humans' logical inference capability into the system. But now, I think another area that I actually share with my technical community was that you should think about so think about recognition. Don't think about just the acoustic data, right? There are a lot more information you can use. You can have a facial expression that helps recognition and understanding, right? And you also have you can that's called a multimodal communication. The shape of the mouth can help, and then you can actually get some text information that also help. That's part of the language model. There are a lot more than language model. That information can be actually aggregated in order to do kind of ensemble learning to help on whatever task that your speech recognition. Like Alexa, for example, they actually can, ideally now Alexa, it's pretty unsophisticated, right? You use Alexa, you ask something, very often they say, I don't know, right? I don't have the answer. They use the all time. So for example, my Alexa is on. Every time I say Alexa, my Alexa is on, right? It's not very intelligent at this point. But there are a lot of opportunities. You have to use multimodal data to use, for example, if Alexa knows that I'm giving a talk, especially, I'm an expert in speech recognition. I was talking about, when I say Alexa, that could be technical Alexa rather than looking up Alexa. Right? So there are a lot of information you can integrate. So one of the lessons I learned from finance world is that even if you have very weak signal, in old days in speech recognition, usually I throw away. So when I combine, many people think that, well, you get hidden macro speech recognition, you get neural network speech recognition, you combine them, you get it, because they're very different kind of model. When you combine, you probably get a result. No, that's not the case. If we combine them, hidden macro model really automatically play no role, because if the error is much higher there, if you combine it, you don't get over again. Whereas in finance world, it's different. You get strong signal, you can weak signal can still contribute through the ensemble learning, and that's really what ensemble learning theory at work in finance. Where in speech, I never found that work to be the case. And part of the reason would be that, in the old days, people used just acoustic signal as input for recognition. You have different architectures. The macro model, neural network, deep neural network, fully connected, convolutional neural network. You get, transformer. You get, other kind of sophisticated. You combine, you ensemble them. One is stronger than other, and whereas the input is the same. Therefore, when you ensemble the output of different architecture, it actually produce the output which are correlated with each other. If that were the case, normally you don't get as much gain through ensemble learning. I don't know what the theory says, but that's empirical experience is all the whereas in finance data is very different, right? Because typically different sources of information come from different data. And then you can use the different or the same kind of architecture to get something which is less correlated at the output. Therefore, we need something to. And so I advise that some of the maybe the key lessons I learned is that you should go back to look for more different sources of input that help you to do the kind of either Alexa or Cortana or Apple Siri, all kind of devices. Take more information. Take information about the speaker. If the device knows a little bit about the speaker, knows that you're giving a lecture rather than using the service, if they shouldn't turn on, they should, maybe, give you a little bit different way of feedback. I think that's important. That's part of the lessons I learned through the first challenge of heterogeneity of data. And of course, for other kind of challenges, there are different kind of, guidance that may help to advance natural language processing and speech recognition still they are. And due to the time limit, I'm going to stop right here. Thank you very much.
All right, let's thank Lee for the interesting talk. So we do have one question so far in the chat box, which I'm going to read out loud. The first question is from Min Tring. The question is, what are the best methods to make deep learning models explainable in finance?
Well, unfortunately, this is something I don't think we work on that, of course. There are some architecture there that so I won't be able to reveal any specific technique because a company, it's a finance company. Usually they don't openly talk about the technique. But at a high level, the answer is that number one, the problem is very important. It's a bit like a medical domain, right? If you make a lot of money for your investors in the finance industry, people normally don't care about how you make money. But if you lose money, they want to know why, right? So there's a very large obligation from compliance viewpoint. You need to provide the answer. So the old days, you know, maybe not so much, at least by the time I joined my company, well, you know, I get to find that, you know, many of the techniques used in doing financial predictions they're heavily dominated by linear model. And one of the selling points of the linear model is that it's explainable. You can just look at the weight there. You can know what kind of term, you know. And I personally, you know, I won't be able to give a specific answer, but, you know, most of the techniques that in the neural network literature nowadays, they try to do explanatory, you know, work. You know, there's some, you know, workshops, and some of those we actually explore them. And not everybody, not every candidate is successful, but some of them are. So my high-level answer, without revealing, you know, any detailed technique, is to say that you read that the literature, it's useful effort. It's not going to be wasted if you read, you know, all the, you know, literatures in Europe or in HTML or explanatory or AI. Yeah, thank you.
Okay, thank you. The next question, so we have a lot of questions actually. The next question is from Jitendra Mathol. The question is, what are your thoughts on computational limitations of deep learning? What are the most promising alternatives?
Yeah, computational limitation, I think just, you know, people now building chips, right? You know, to do deep learning. So the limitation really is, I personally feel that academic, you know, may have disadvantage on that one. You cannot have large tasks to get all this. So I personally don't see that. I still don't see the limit about having more data for supervised learning problem with clean output. With the noisy output, like, you know, finance data, I don't think that trend is going to go on. But for now for recognition, now the error rate drops so much, right? You know, and when you talk to Alexa, normally I would never get any errors there so far, right? And they use the Google search, you know, Microsoft used to have, you know, Windows phone search. So the trend still will continue. You get the bigger data, you have a good label, you get bigger, the error still can keep dropping. I'm pretty sure it would drop, you know, in all the tasks we know about, as long as the label is clean, is clear. You know, having more and more data and label them well, and then having more compute, the error can drop. So the limitation, I just don't see the limit at this point in time. But computational limit is, you know, how much, you know, can afford to buy, and that become a completely different industry. So what's the second part of the question? What's the future of overcoming the limit?
Sorry, the question was
the second part of the question.
What are the most promising alternatives?
Oh, well, I don't know. You know, I think it's a good direction to build, you know, customized chips, right? You know, the graph core. You know, I don't know, when you go to Europe, last 2 years, graph core was a very dominant one. I think all this hardware, I think they are really worthwhile. I'm not saying that, you know, their stock are going to be big, right? But the demand is there. But I still see many applications that I haven't worked on that can transform this kind of, as long as you are very smart in labeling your output data cleanly. And that's the art, that's the industrial secret, right? So if the labeling using whatever, you know, ingenuity that you can come up with to label that. That's in old days, right? In speech recognition, we actually don't just have people to label data directly. There's still cost there, right? So typically, when you say something on the phone, you know, many years when I work on Windows phone, right? At that time, now it's gone. And then if you ask them a question, if there's an error, it doesn't give you the right answer to click, then we treat that to be wrong answer. It's throwaway data. But if you click and then it performs, you know, the right thing, you know, the user doesn't, you know, doesn't get upset or whatever, you know, means we can to be the right click, and that's actually cost-free way of getting the label data. And I believe that there are many industries still around, maybe maybe in the doctor, medical industry, that's what I'm thinking about. It might actually have similar kind of benefit if you can figure out the challenge is not really computation, it's not the size of data, the cost of labor. It really is how to use your imagination, your invention to label the data during the natural use of the algorithm, and then you can decide which data, active learning style of data collection. If you can do that, then I still think that there is a long way to go using the standard large neural network, large data, large compute to get better result for unsupervised learning paradigm.
Okay, thank you. So because we have a lot of questions, I'm gonna just ask a few that are more technical in nature. So one is from Tamir. The question is, could you speak a little more on how you deal with non-stationary data in high dimensions?
Yeah, so you're talking about speech or talking about finance? Finance, right, I suppose, right? Yeah, so non-stationarity, yeah, actually I have some slides over here about this. I skipped all of it. So one key difference between voice recognition and finance is different ways of handling non-stationarity, right? In speech or in many other machine learning types, in image or maybe even autonomous driving kind of scenario. You have training set, you have validation set that helps you to tune hyperparameters or maybe doing other kind of validation, and then you can go to test. Sometimes you can use the test a few times, right? You don't limit yourself. Like in my speech, a timid task, and in my script, experiment script, I actually most of the people do the same thing. Training, error, validation error, and test error, right? You just you change your hyperparameters. You can see that until your training error drops to almost zero, and then you see that validation sometimes up and down. And then for speech, for that particular task, and also in many tasks, I found that validation and test data usually they don't change too much, right? Usually validation is slightly better because the hyperparameter is tuned, but the test it may not be. But if the statistics are not differing too much, sometimes you use the test data a few times, it's okay, right? Especially for publishing papers. Now for real world, it's different, right? So, but actually in real world, it doesn't hurt too much either, right? People, do test it. But in finance world, we can only do tests once. If the first time test work is not good, then you throw away all the technique. You have to start from scratch because that means your system may gain something out of your use of test. But because of non-linearity, it gives much more stringent criteria for doing. We call the back testing. Right? Typically, you don't do that more than once. Sometimes you do occasionally. It depends on the scenario. Right? If something very very quick, you understand that market is very competitive. Then you should be much more conservative because of the nature of non-linearity with the competitive nature. The criteria for doing validation and testing, it just has to be much more conservative. High-tech tasks I've been working on. Yeah.
Thank you. Another question is from Tao. The question is, what kind of role does causal reasoning play in financial deep learning?
Well, I won't be able to tell you much. It's useful. I won't be able to say too much about this. Causal reasoning, it looks like economic, right? It's kind of causal, but the causality is very complex, right? You don't know. I mean, if the Fed raised the rate, affect others, or if or the other one affected the. So it's complex. Yeah, I just want to say it's complex. And there's a role to play. Yeah.
All right, thank you. Next question is from Robert. How much additional performance can we get out of further scaling up the data without multimodality?
Without multimodality, I personally feel we're talking about speech recognition, right? So I personally feel that I mean it's the low hanging fruit has all been picked already without using multimodality. People have reached very, very high level. Except you are dealing with multi-speaker speech recognition, that's called cocktail effect, and there's a good research to be done. I have seen recent papers on that. Because first of all, you don't even know what is input, right? You have two speakers together. Humans a human can focus on the attention to one speaker, ignore the other speaker, even if the interviewing speaker have louder voice. Right? Human is very good. You know, to the cocktail party, you know, somebody is shouting very loud, but you are focusing on your friend, and then you can ignore the shout speaker. And computer so far is not able to do that. The standard algorithm pick up the largest, you know, volume, and then track that speaker, and maybe it's the wrong speaker there. So I think in this area, still large data, but you have to use a different algorithm, different architecture if you read the literature. It's very, because standard architecture, you don't even know what the right output you can get, right? So in that area, I think, but of course, multimodal still can help. But I think that for the straightforward voice recognition, I personally, you know, if I want to research, I wouldn't research on that area without using multimodal, because, you know, it's just long hand. It's just, you know, most of the tools has been squeezed, right? You know, putting effort in there, I personally wouldn't do it. But maybe if you, I mean, it all depends on application, right? Maybe some resource powerful language, certain kind of speech minority, you know, for government sponsor, you know, but commercial system normally don't invest a lot on that.
Okay, thank you. So another question is from Jen Chi. So the question is, since the traditional stochastic models like the Black-Scholes model rely on many strong assumptions,
Yeah.
can deep reinforcement learning without any assumptions, I guess, probably outperform traditional stochastic financial models?
Yeah, I do believe so. Yeah, I actually, I personally, I learned that theory, you know, after I joined the company, and then it turned out that there is so much. The standard, you know, Black-Scholes model doesn't seem to work well, right? Everybody knows that, and there is a whole bunch of improvement on that, you know, for option kind of trading. I personally feel that, you know, if you throw away that that kind of you know, modeling, it may, you know, I think more likely it can produce a little better result. Unless, you know, you have some special kind of you know, ways of handling the theory. Maybe if the data is very limited, then maybe. If there's a large amount of data, I think that the model has so many assumptions there. You may as well not use it. But on the other hand, if the data is small, it's the same philosophy in deep learning. If you put small data, you put in knowledge there. The knowledge is reliable, you get a good. Knowledge requires a lot of assumption. If they are wrong, then you're not going to get much. So I think the same philosophy. So think about, you know, Black-Scholes model as one very crude approximation to you know, to what real world is, right? So for very small amount of data, it may work better. But for large amount, I prefer not to use.
Thank you. The next question is from Shabam. The question is, can you give some examples of weak signals which are valuable in finance?
Yeah, I didn't hear
that. Can you give some examples of weak signals which are valuable in finance?
Well, I won't be able to say that, right? And this is our signal, right? But I can say a bit open signal, right? People discussing in the literature, in the books, right? So for one very weak signal that may be useful. Well, I know that weak signal was very useful many years ago. Like whether the weather is, if it's today sunny versus raining, then that's one signal. Right? It can affect, you know, you know, the trader's mood or something. It's very, very weak. Like it's so weak that you might as well throw it. But I heard that nowadays it's not going to be. But people use that as a typical example, without revealing any other kind of. But there are many examples like that.
Mm-hmm.
Yeah.
Thank you. And let's see. Okay, so maybe two more questions remaining. So one is from. Okay, well, three more. Let's see. First is from Oscar. I guess what the question is, how do you detect and remove biases in finance models?
Bias?
In terms of fairness, I guess.
Yes. Well, you're talking about trading. Yeah, I'm not quite sure. I mean, in fairness, in terms of trading or in terms of you know, investors. Also, yeah, there are some biases. Yeah. I don't.
So Oscar, if you want to chime in and clarify, please feel free to do that.
Okay. How about next question before I clarify what bias?
Okay. All right. All right. Maybe let's move on to the next one. So investors. Okay, I'm not sure. Okay, all right. So next question is from Ali. Can you talk a bit about the kinds of smart regularization employed along the lines of Black-Scholes question and the possible assumptions from traditional methods?
I don't think I can say all the details about this. But the high level is that I mean, speaking about my own experience, right? Sometimes I learn a great deal from real experts in my company. Well, this is one of the best companies around. Once I look into the way they are doing the way they are doing things, right? They don't think about a lot of mathematicians, physicists are doing trading. They do their own things, right? They don't even use the language of regularization. So I look at it, wow, how do you do that? Oh, that doesn't make sense, right? Because training and testing, training linear model, they have very different methods. They can use a completely different objective function. So what that doesn't make sense, right? In voice recognition, the training objective function and test objective shouldn't differ too much, right? The only thing that differ maybe a recognition term, right? Training you add recognition term, that the testing, you don't have a recognition, you just use original cost function, to do it. And then in financial world, the difference is so much bigger than I ever thought about, ever seen in machine learning literature, right? So like drop out, maybe many people would think that, well, when you do the drop out, you don't use the cost function, you actually add some data dependent regulation, which can be implemented by doing drop out procedure, right? So that's a little bit, and people understood that later on because it can make the model more robust, whereas in financial world, and there's a much bigger difference between whatever objective function in different in the sample domain and ultrasound domain, and that's all I can say. Exactly how it is, and then I have to take initiative out of my own to translate whatever I found into machine learning terms to understand. Wow, that's equivalent to having this kind of regularization. That's why I call smart. And sometimes it works well, sometimes it doesn't work well. Sometimes it's data dependent, sometimes it's the model dependent, sometimes it's this dependent or that dependent. And then I try very hard to understand what kind of economic motivation it is behind this one. And maybe for experts, they just use that as their tool in their toolbox for many years. They never thought about this in terms of machine learning terms. So that's why I call it smart. Smart means that sometimes it's not easy to directly see the essence of what they are. It requires certain. So again, details I won't be able to reveal, but just to share at a high level that in order to handle extremely high noise, especially at the upper level and also in the input layer level, very different kind of regulations I have ever seen in machine learning literature so far. May work better than otherwise. Yeah.
Okay. So, I mean, we got a clarification from Oscar.
Yeah.
I'm not sure if it makes sense though. I guess he was talking about cognitive biases in finance and in terms of behavior finance, right? So I guess your risk, tolerance may be, distorted, perhaps, right, for the different investors.
Okay, now I understand that.
Right.
Yeah, I understand the nature of the question now. In terms of different investors will have different return and that kind of bias, how they affect.
Right.
Well, so I won't be able to say too much. Except at a very high level, I would say that once we understand the tolerance, risk tolerance level, so finance really is the same as in. Well, actually, one of the things So as a side track for this question, to answer this question, one of the things I would let you know that this is one of the things I discovered. It's interesting, right? So I have been doing signal processing, for many years, including microphone array, and then in financial world, there's a corresponding problem, which typically I didn't realize until I worked on that. It's called portfolio optimization, right? The one I showed you the diagram there. So portfolio optimization really to trade off between risk and return, right? So they optimize the ratio of the return versus the risk. And risk, have risk model there, and the return, it's coming from whatever different model, alpha model, or they all come back together. So risk and return. So when people have different risks, as a side track here, I just out to share with people that for those people who are working on some other kind of machine learning problem, especially, so I found that so return versus risk, when you optimize that, you actually essentially you solve this convex optimization problem. You can get a precise solution for the allocation of portfolio, right? And that's a standard formulation. It's called the mean variance optimization. And then if you some nonlinearity there due to some other factors, other models, things become complex. But in pure form, that was the Nobel Prize work in by economists, how to do optimal portfolio. And that algorithm is exactly no single difference from microphone design in terms of how to optimize the gains for different microphones. So the gains for different microphones, for example, I think in most of the phones they have 4 microphones. It's like a four stocks in the portfolio, right? If it's 7 microphones, you have 7 stocks. So the gains automatically turn on for different microphones. Actually, it's also trying to optimize the ratio of the signal versus noise. And noise is measured by by some averaging or whatever, and the signal is the one that that's detected on speed. So you optimize the signal to noise ratio for microphone. Actually, there's a solution that happens to be exactly the same solution as portfolio optimization. But after you add nonlinearity there, do some analysis become different. So I'm saying that for the bias, the risk, different investors may have different risks. Once you understand risk, typically, you design the optimization specific for that client, right? You just change your risk, model that can be compatible with the risk tolerance for this particular investment, and that bias can be reflected into one of the terms of the optimization process. Maybe if that is not the right answer, let me know. Well, unless I understood the bias to be wrong.
Yeah, I think the question was answered. Thank you very much. We're out of time, unfortunately. So let's thank Lee again for the great talk.
Okay, thank you very much. Appreciate it.